Welcome guys, back to another video on conic sections. Today we'll be examining a problem about ellipses and the lines tangent to ellipses. In the problem, we're given an equation for an ellipse in Cartesian coordinates. It goes as such: x squared plus 4y squared equals 1. We can of course standardize it a bit and draw out the ellipse as shown here. It will have a center of the origin, a major axis with a length of 1 being on the x-axis, and a minor axis with a length of 1/2 that lies on the y-axis. And of course, we're also given a line in the form of y equals mx plus 1, and we're also given that it intersects the ellipse at only one point. There is a unique point of intersection between them. So there's actually going to be two such lines here. There's going to be one that ascends to the right. It will have a positive slope, and there's also going to be one that ascends to the left, also tangent to the ellipse at one point. And their slopes will actually be identical, right? Because the ellipse is a symmetrical figure. It's basically like reflecting one of these lines over the y-axis to get the same point of tangency and basically align with the exact same slope. And so we're asked to find the absolute value of m to remove this ambiguity. And since there's only one point of intersection, there's only two such lines with identical slopes, there should really only be one value for m, which makes this m right here not a variable, but more of a coefficient for the x term. I'm saying this because we usually solve such equations. We usually look at these intersecting curves as a system of equations in terms of x and y as the variables to solve for x and y to find their intersections. And because there really should be only one value for m, we should be able to solve this system. Because we couldn't solve the system, for example, if we had a line that intersected the ellipse at 2 points and also went through 0, 1, right? There will be uncountably, infinitely many such lines. There could have ones with a steep slope, with not so much of a steep slope. They would all satisfy those two criteria. So technically this should be possible, and we can attempt to solve it as just a system of two equations. So let's try to do that. First, we can obviously substitute y into the ellipse as mx plus 1. Look at the equation for the ellipse. We get x squared plus 4 times y squared. Y is mx plus 1. We square that. That's equal to 1. Let's move on. Let's open it up. We get that x squared plus 4 times m squared x squared plus 2mx plus 1 is equal to 1. Right? Then we open that up as well. X squared plus 4m squared x squared plus 8mx plus 4 is equal to 1. And if we move the terms around to make this a standard quadratic, we will get that, seems like, yes, 4m squared plus 1 times x squared. We factor out x squared here, plus 8mx equals, no, plus 3 is equal to 0. There we go. That is our standard form quadratic. And I did this to I made it a quadratic in order to emphasize that m is in fact a number. It is a coefficient, it's not a variable. We should be able to solve for this regularly. And really, again, the main thing here is that there is a unique point of intersection with the ellipse and with the line, right? If there's a unique point of intersection, that means this quadratic equation only has one solution. And how do we know if an equation has only one solution? We know it by its coefficients. These coefficients of the terms must make up a discriminant such that the discriminant is equal to 0. And so remember that the discriminant is equal to b squared minus 4ac, b squared minus 4ac. And if it equals to 0, there's only one solution to this quadratic. So we can basically just set up a quadratic for m to find that value of m. So let us do just that. The discriminant of this quadratic right here with these coefficients in terms of m will be b squared, so 64m squared, minus 4 times a, 4m squared plus 1, times 3, basically minus 12 times 4m squared. And we have to set it to 0 because that is given to us that there is only a unique point of intersection. So if we solve this, if we can open it up a bit. It's going to be 64 m squared minus 12 times this, right? So 12 times 4, I believe, is 48. 48 m squared. And also minus 12 times 1, so minus 12. That's equal to 0. Of course, we get that 12 m squared, right? No, 16. Yes, 16 m squared is equal to 12. And of course, m squared is going to be 12 over 16, or 3/4. Therefore, the absolute value of m is going to be root 3 over 2. There we go, and that is the answer to our question. And just like this, using a discriminant, setting it to 0, we are easily able to find the value for m, because there really only exists one such value for m here, if it intersects at one point, like I was saying here. That is the main moral of today's video. And of course, now you know m, you can keep solving this quadratic for y and x to actually find where the line intersects the ellipse. And you can do that if you wish, but that is not in the problem, so I will not. And that's it. Thank you for watching.